Lecture 5.3, charging a capacitor. So we need to identify certain circuit symbols. So circuit symbols that we will be using. One is that we have a source of energy in an electrical circuit. And this is what we call a power supply, but for right now, you'll either hear me say power supply or battery. But what I'm really saying is that this is the source of all energy. And the way I'm going to draw these is that I'm going to draw them like this. I'm going to draw a little circle. And by the way, this notation is not universal. And then I'm going to put a plus and minus sign. And then I'm going to say that this is the source. This is the battery. And so what you're seeing here is that up at the top, the plus sign is called the high. The bottom here is called the low. And the other symbol that we want to look at is we want to look at a capacitor. And a capacitor, which we have been drawing, this is a universal symbol. And I'm assuming that we have some dielectric that is not air. So this will be the symbol for a capacitor, which we label as C. To move any charge requires a potential difference or in circuits, we typically call it a voltage. So it's not a difference in voltage, it's voltage produced by a power supply. And yes, this is the battery. So picture-wise, we then have something, we want to look at what this statement actually means. So if I have a battery and it's connected, a battery, what it's going to do is it's going to, of course, to supply voltage to the circuit. So what do we mean by voltage to the circuit? So what we mean here is that it supplies an incline. And so if I look at this incline, I'm going to say that this guy right here is going to be my incline that looks something like this. So when I look at this, I am seeing here that now I have my incline that looks like this, which is what the battery produces in the circuit. So this is my upper plate, same notation that we've been doing. And so then this end here is our positive plate, which is our high. And then down here is our negative plate, which we call the low. And so when we're talking about the low, what we typically define this here is that we typically draw a little symbol like this, which means ground. In other words, it's at 0 volts here. Everything is measured relative to the ground. So then I come up here and I just say, okay, this is the voltage of the source. And of course, this is our electrical height change right here. That's what we mean by that. So if I have a high and low, potential, then what I'm going to have here is that I'm going to have charges that already exist in the circuit, and these guys are positive charges that are moving. And the reason why they move here is because there's a potential difference. There's a height change. So then we say that this right here is the direction of current. Current flows from a high potential to a low potential. That's what we mean by electrical current. When do I not have current flow? So you know what, before I forget here, let me do this. So if there is a voltage, which means that there is a height change, so we then say voltage causes current. So this is our cause, and this is the effect. That's the cause and effect. Now I could have something different, and I want to compare this to this situation. I could have two plates that look like this. So if I look at this, you can see here in these plates, there's no height change. So if I look at this thing, and we can say that both of these are on the ground. They're down here at the bottom of the incline, and they're on the ground. So guess what? There's no charge difference between them. So if I place a charge right here, what you're going to see here is that in this case, there is no motion, which means no current. On the other hand, I could have the exact same situation as this, but now it's not on the ground. It's at a high potential here. So in other words, these guys now are higher from the ground. So remember, this is how I do that. So for example, let's say that this guy here has, this is at a 15 volt height, this is at a 15 volt height, which then means that on this plate, I have negative charge. On this plate, I have, let me be careful. I don't want to say negative charges. I'm going to get into trouble. But I'm higher up. So the same thing actually happens. In this situation here, I also have no current because there's no incline. So what I could say here is that if I have no voltage, in other words, no height change, so no voltage causes no current. So if you have no voltage, you can't have a current. So I probably shouldn't say cause. I should probably say if there's no voltage, there's no current. So I can have different voltages on these plates, but if there's no voltage across them, there's no current. Now let's apply this to the capacitor circuit here. Now, applying this to a capacitor or a capacitive circuit, it means something like this. So if I have a battery here, and it is now connected to a capacitor, And what we're seeing here is that I have a source voltage that sets up the incline. Here's a capacitor. So current will only flow if the voltage of the capacitor is not the same as the voltage of the battery. In other words, in this situation, I will have current that moves. So what I'm saying is this, is that if the voltage between the battery and the capacitor is not the same, that means that we have a potential height change. In other words, we're talking about this circuit right here. If that's the case, then I'm going to have current flow. So charges will move, and as a consequence, we then say that now we are charging a capacitor. On the other hand, if I have this exact same circuit here, okay, so now I'm going to look at this scenario here, but this time it's changed now. What happens now is that when this capacitor is equal to the battery source, then what we're going to find here is that there's no current. That means that the power supply and the current have the same potential. So in this situation, we then say that if the voltage of the source is equal to this, then we have no potential height change, which then implies no current flow. And this tells us that we now have a fully charged capacitor. So in this situation, we're really looking at this guy up above, but there's no current. So this is what we mean by all of this right here. So now let's go look at the three stages of the capacitance of charging. So there are three stages in charging up a capacitor. So what you're going to see here is that there's going to be, I'll put in three states. So I'm going to copy this because I'm going to want this. And here, and then I'll modify. So the first stage that we'll have is I'm going to say that this guy here is the initial state. So what happens in the initial state? So if I look at this circuit, the way it's typically drawn here is that we imagine that there is this thing called a switch. And what we know here is that at t equal to 0, I now have a complete circuit. And so what I do know here is that right before the switch is thrown, this is 0 since no charge is on the cap. So now what happens next? What happens next here is that we go to what is called the transient state. So in the transient state, charge is now flowing. So if I look at this thing, here's what we're seeing. I have my circuit just like this, but now what we know here is that there's current flow because the potential difference between these two is not zero. And then we're going to get to what's called the steady state. And then we finally get to the third state, which is called the steady state. So when I look at the steady state, then I have this circuit, but the big difference now is that it's now going to look something like this. These guys are equal. And now the current is equal to zero. So there's no current in the circuit. And what we're seeing here is that we have some buildup of charge, but over here, we have a fully charged capacitor. That's the three stages right there. So now let's go into more details. So what do we know about this thing? We know this. Initially, the capacitor is uncharged. That means here that Q is equal to zero, but if Q is equal to zero, then the voltage of the capacitor, which is given by charge divided by the capacitance, that's also zero. So that's what we mean when we say we have an uncharged capacitor and it's at the bottom of the electric incline. So to see this picture here, I'm going to come in here and I'm going to paste this guy back into here. And so when I look at this circuit, what am I actually seeing here? What I'm seeing here is that right now, this guy is equal to zero. There is no charge. Okay, there is no charge. So when I come and I start to look at my charges, they're everywhere in the circuit already. I don't need charges. They're already there. As soon as we turn on the power supply, now charges move everywhere in the circuit. So as they move, what you're going to find here is that we have incoming charge. Just like we said before, we have outgoing charge. And the way we depict this thing is we use our incline because it's hard to visualize this process here. So if I look at this thing, what I want to do here is that I want to look at this guy and show you that there is a way to visualize this. And the way we visualize this thing is that now we set up an incline. So I have my plate right here. and then I have an incline. So when I look at my incline is coming all the way across, and then I have my other plate right here. Now what the battery is doing, it is setting up this incline. That's what we mean by that. And so the battery does this, and as it does this, we now have a height change of the incline, which is of course of the battery, where now we set this to 0 volts, and that's what we call the ground. Now the battery already has a high potential. So that means it has a bunch of positive charge, and that sets up the high part of the incline. And then we have the bottom here, which then sets up the low part. So where is the capacitor? Well, it has no charge. So it has to be down at the bottom because it has 0 voltage. So then I'm going to come in here and I'm going to say that here is my capacitor. It's at the bottom. And because it's at the bottom here, it has no charge. But as soon as, so what we're saying here is that I'm saying this, that this guy has no height. But now what happens is that I have lots of charges on the incline. And so what are these charges doing? These charges are now moving down the incline and piling up. So we're seeing these charges moving down. So if I start to look at this thing, then I'm going to say, what does current flow mean for a capacitor? And the reason why that's an important question here is that the dielectric inside the capacitor prevents any current from passing through it. And the reason why is that it acts like a hole in the circuit. So what I mean by this, so if I have my circuit, let me see if I still have an image of that circuit. Good. So if I have a circuit like this, what I'm seeing here is that when I see a capacitor like this is effectively looking like this here. Its whole goal here is that when we talk about current, we're talking about current flowing, but there's a hole right here. That is a hole. In other words, this is a hole in the circuit. Where charges cannot jump the gap. So current through a capacitor is unique in circuits, right? So I should probably put that through a capacitor is unique in circuits. No other element does that. So what do we mean by current? So in this situation, we say that the rate of charge being placed onto the upper plate is exactly the same as the rate leaving the lower plate. So then picture-wise, we have this. We have a plate. Remember, that dielectric in there effectively creates a hole. Even though it looks solid, it really is a hole. So when I'm looking at this guy, what we mean by current here is the following thing here. I have a positive charge being distributed. So when I'm looking at these charges are coming in, right? And it's positive. So what we're seeing here is that we have an incoming charge. But at the moment that that charge lands, there's another charge simultaneously leaving the bottom plate. So we have this outgoing versus this ingoing. And so what it says here is that when we talk about current, that means that the rates are exactly the same. So what we mean by current then is then we say that the incoming current equals the outgoing current. So these currents are the same. And because they're the same, we could then say it gives the illusion that current is moving through the dielectric. It's not, but it feels like it's going through it. So then we continue to move on. So as the capacitor builds up charge on its plates, it increases in voltage. This means it is climbing up the electric incline. So picture-wise, since we've already drawn this, let's steal this one right here. So I'm going to go from here and copy this and bring this guy down. So now what I'm seeing here is that I have to change the capacitor here. So what I'm going to do is that now I'm going to erase this, and I'm going to come in here and move this capacitor. So where I'm going to move it is that I'm going to move it to right here. So oops. So I have my capacitor, which is now has some amount of charge. So when I look at the amount of charge that it has some that it's still, it's not all the way up, but it's has charge on it. But note, we still have current flow through the capacitor. So what I'm seeing here is that I'm seeing this, that now this guy has climbed up here. And you could see that it's climbed up a certain height. Now, the thing to really pay attention to is this quantity right here. It's the difference in height. So when I look at this guy, there is a difference in height. And I'm going to say that this is the difference, which is then going to be the difference between the source and the difference between the capacitor. And what you're seeing here is that now that difference has decreased. So let's write that up. So now there is a smaller voltage differential between the battery and capacitor. Since this voltage difference is smaller, there is less electrical push. On the charges in the circuit. So what does that mean? So I first started out with a larger voltage differential. And so what that means here is that this guy was, the difference between them was big because essentially the source and the capacitor are radically different, right? It's effectively zero. So as a consequence, I then had a higher current. But now, as the capacitor is charging, there's a higher voltage differential, which then means that the difference between these two is now decreasing. And the reason why it's decreasing is because the voltage of the capacitor is increasing. As a consequence, there's a lower push on the charges, and so now the current starts to decrease. We have a lower current. So let's physically, talk about this before we move on. So physically, this makes sense from the cinema and cinephiles analogy. So when the cinema opens the doors, the cinephiles quickly rush in, causing a high current. After the initial rush, the following cinephiles have a harder time finding good seats. Therefore, this causes a lower current. This is what effectively happens in a capacitive circuit. The capacitor ends up with the lower current because it's harder to put charge on the plates. At some point, the circuit reaches a state of equilibrium. Called the steady state. When the voltage difference between the source and the capacitor is exactly zero. Since there is no height change, between the battery and capacitor no more current will occur. In other words, we have zero current. The capacitor is now fully charged. So picture-wise, we should come back and steal this guy right here and then modify it. So if I look at this guy, I have this scenario right here. So now what's different here? Well, we're not going to have any more charges here. So if we don't have any more charges, then this is what we're actually seeing here. The capacitor is now at the same height. So when I'm looking at this capacitor here, I'm seeing that it's at exactly the same height. So if I'm looking at this, then we're going to say here is that this guy right here is now the voltage of the capacitor. They're equal heights. So when I look at the voltage difference between these two right here, it's exactly zero. So now if I look at how high these guys are, I'm then going to come in here and I'm going to draw them like this. I'm now going to say that I have my capacitor. And then I'm going to look at my plate. So when I look at my plate, note that my plate has how much charge? So I'm going to say it has this much charge. And now my incline is now flat. And so this guy effectively has to have the same amount of charge. So now we can see here is that the difference between these two is zero. So when I go and I measure them, everything has to be measured relative to the ground. So then we could see that this height is that, and finally, this height is exactly the same.